Hello again, welcome back. This is video lecture 10.1. We are starting chapter 10, which is the first of a two-chapter sequence on rotational motion. So, not surprisingly, chapter 10 is entitled Rotation. The reading for this video lecture is chapter 10, section 1, in which we're going to define all the useful rotational kinematic variables, the rotational version of all the kinematic variables we studied in chapters 2 and 4. If you recall, to study motion in chapters 2 and 4, kinematics, we introduced position, displacement, velocity, both average and instantaneous, and acceleration, both average and instantaneous. And for every one of those linear kinematic quantities that we've talked about, there's a rotational analog, a rotational cousin or version. Now, what I mean by rotation, to be specific in this chapter, chapter 10, is a rigid body. So it's, well, the name rigid means that it really can't, we're not going to be able to deform it. Okay? Its shape, its overall shape isn't changing. And it's rotating about what's called an axis of rotation. And that axis of rotation itself is not going to move. So an example I'll attempt to show you with the video camera on my laptop is, in essence, a bicycle wheel. Okay? Here it is. Okay? It's a bicycle wheel that we just haven't put on a bicycle. Instead, we've mounted a handle where the central axis would be. And then if I hold the handle, it's got what's called an axis of rotation right through the middle with nice ball bearings so that it turns quite freely about the axle. Okay? That's a rigid body rotating about a fixed axis of rotation. That's the topic of chapter 10. What would be a moving axis of rotation, you ask? If this is going like so, and then I move the actual axis, the handle I'm holding, like this. That's a rotating body about a moving axis of rotation. That's a bit more complicated. We'll save that for chapter 11. So for this chapter, it's a rigid body like this bicycle wheel, rotating about an axis of rotation, here in this case through the center, that isn't itself moving. What do you observe in such a case? Well, what I've done is, it might be hard to see, but I have drawn a little, on a piece of paper, a little red dot, and I have just taped it to one point on the wheel. And as the wheel rotates, what does the dot do? Okay? What is the motion of the dot? It's just a circle, isn't it? So if you take any particular point on the rotating wheel, it just moves in a circle of some radius, depending upon how far it is from the axis of rotation. Now, I show the wheel rotating in a fixed direction at a fixed rate. That's possible. Right? As I look at the wheel, it's rotating counterclockwise relative to me, as you would see it on the video. I can't tell from here. Okay? You can decide for yourself whether it's clockwise or counterclockwise. It depends on what the video camera's doing. But I could turn it to me, so that to me it's looking rotating clockwise. So it can go clockwise or counterclockwise as we look at it. Those are the only directions. And it can slow down, like if I put my hand on it, and then it can go back the other way, and then I can slow it down, and then I can have it go this way, and I can speed it up as it goes. So it's pretty complicated motion that we can get to have happen. But it's all rotational motion about a fixed axis of rotation. That is what we are interested in studying in this chapter. Okay? All right, so to do that now, let's go through one by one and take all the kinematic quantities we introduced in chapter 2 for linear motion along an axis and talk about the rotational version. Heads up. In rotational kinematics, all the kinematic variables are represented by Greek lowercase letters. Not letters of the Roman alphabet, like V and A, but letters of the Greek alphabet. Then we got to be aware of that, okay? So you're going to hear me say a lot of Greek letter names. So let's start with our definitions of the rotational variables. First, let's talk about just what we call angular position. We need to be able to denote where that red dot is, for example, on our rotating wheel. Right? We're going to pick a point, if you like, on the rotating object, and we're going to keep track of where that point is as the object rotates. And so by angular position, we mean the angle between a reference line on the rotating body and a fixed zero angle line. So let's go ahead and refer now to this picture that I have sketched here. You can think of this as just representing the rotating wheel. And I've got a horizontal x-axis, used to that, and a vertical y-axis. And the axis of rotation, which was that central axle through the middle of the bicycle wheel that I was holding, is that dot that I've just drawn there at the origin. That's where the axis of rotation is, and it's coming right out towards you. And then I have represented the red dot that I showed you on the wheel with a red dot there in the drawing, and I've called that point P. And I've even drawn a red line connecting point P to the axis of rotation. Okay? So what we want to keep track of is that red reference line. What is the angle between that red reference line and what's going to be the fixed zero angle line, which is going to be, by convention, the plus x axis. Please, let's be clear. Those x and y axes that you see are not rotating with the wheel. The wheel is rotating about the axis of rotation through its center, and therefore point P is going around and around in a circle, but the x and y axes are fixed relative to the ground. Okay? So by the angular position, we're going to mean the angle between the red reference line on the wheel and the fixed plus x axis. And so, sure enough, right there, the diagram shows the angle that that red line makes with plus x and labels it with a symbol that's a Greek lowercase theta. That's what we're going to use for angular position, the letter theta. And the angle here in this picture, as you can see, is measured counterclockwise from plus x. I go counterclockwise from plus x to get to that red line. And by convention, if the angle is measured counterclockwise from plus x, it's a positive angular position. Conversely, if the point P had been, say, down here, at the moment I drew the picture, with the red reference line from the axis out to where it is, then get back to this, okay? Then I would have measured the angle that way, the theta, and that's clockwise from plus x. So by convention, that's a negative value for theta. Theta is positive if it is measured counterclockwise from plus x, and it's negative if measured clockwise. Okay? All right, some other things to note from this diagram. Okay? The point P, where the red dot is on the rotating wheel, the red dot that is itself moving in a circle, is drawn there, is shown there. The circle is also drawn. The point P at this moment in time can be described by its Cartesian coordinates, x comma y. You would be used to that, I would think, and we even sketched the x and the y coordinates in the drawing. But there's an alternative way to denote the position of that point, and that's to give me, instead of x and y, two other things. The radial distance from the axis of rotation out to point P, which in this case is just the radius of the circle that point P is moving in. That's denoted in this diagram as r, r for radius. And the angle theta that the red line makes with plus x. So I could also, instead of telling you x and y, I could tell you what are called the polar coordinates of point P. And there I would tell you r and theta. So you can tell me where point P is in the xy plane, either by giving me its Cartesian coordinates, x and y, or it's what are called its polar coordinates, r and theta. And we need to be able to go back and forth between Cartesian and polar, but it turns out there's a pretty simple relationship between Cartesian and polar coordinates, just based on trig. Because what you've got up here is a right triangle, right there, with two legs that I've drawn with black lines, and a hypotenuse, which is the red line. And one leg is x, that's this one, and the other leg is y, and the hypotenuse is r, and that angle is theta. So just from trig, we know that x equals r cosine theta, and y equals r sine theta. So that's useful, that's handy to just remember that you can relate Cartesian and polar coordinates. Okay, so at any given time, I can tell you the angular position of that red reference line, which connects point P to the axis of rotation, and it will be denoted theta. It'll be positive if theta is measured counterclockwise from plus x, and negative if it's measured clockwise. What's the SI unit of angular position? It may surprise you to learn it is not the unit of angle that you're probably most used to using, the degree. That is not the SI unit of angular position. The SI unit of angular position is called the radian, RAD. And I will explain a little bit more about that in the next slide. Okay. All right. So let me go to that then. So here I have another circle drawn with its center at the origin of an xy coordinate system. You can think of this as being the circle that our red dot labeled point P on our rotating wheel is moving in, with the axis of rotation of the wheel being that handle that I was holding, being right at the origin. Okay, and so the picture here shows point P. It shows its radial distance r from the axis. It shows its angular position theta. And it shows one other thing. It shows a circular arc here in red, starting at plus x-axis and going up to where point P is. And that distance is called an arc length. And it's labeled here S. S represents what's called an arc length. It's still a length, so its SI unit would be meters. And of course, the radius r is a length, so its SI unit is meters. Here's the actual definition of an angle theta in radians, such as the angle theta you see right in that picture. That angle theta goes with the arc length s and the radius r. And the definition of theta in radians is this line right here. The angle theta in radians is defined to be the arc length s divided by the radius r that you see in that picture like that. And since s is a length in meters, m, and r is a length in meters, the ratio s over r to get theta leaves you with no units at all. Okay? So we say that the radian is a dimensionless unit. Theta has, when defined as an arc length over a radius like this, is in units called radians, but the radian itself is said to be a dimensionless unit. Okay? Note something. If you have the special situation where the arc length s, in a picture like I've drawn up there, is exactly equal to the radius r, you could contrive it to be that way if you wanted, then by definition, the angle theta would be exactly 1 radian. Okay? And in fact, we can figure out how big 1 radian is in degrees. Okay? I will do that down below here in just a minute, so that we can see how big 1 radian is. You probably already have an intuitive feel for how big 1 degree is, because we know that 1 degree is 1/360th of a complete revolution of the circle. But you may not have an intuitive feel for how big the unit of the value of angle of 1 radian is. So let's come back to that. But we may very well have to convert between degrees and radians, or between another unit called a revolution and radians. So let's make sure we can do that. Here's one key thing to remember. For 1 complete revolution of the circle, what's the angle theta in radians? Well, the arc length s, if you go around all the way, is the circumference. That's 2 times pi times the radius. So that's s. And the radius is r. So you can see I've put in the expressions for s as 2 pi r, and then the r upstairs cancels the r downstairs, and I'm just left with a 2 pi. So for 1 complete revolution of the circle, theta is 2 pi radians. So here's the conversion factors you want to remember. All the way around once is 1 ReV, revolution. That is equivalent to 360 degrees, yes, or 2 pi radians. So that's our conversion factor. So let's actually use it to find out how big 1 radian is in degrees. Okay? So 1 RAD, radian. We're going to just do a units conversion. So I'm going to multiply by a conversion factor that is equivalent to unity with the radian downstairs and the degree upstairs. And then we just use this equality here that for 360 degrees, 1 complete revolution, that corresponds to 2 pi radians. So the unit of radian cancels. So I take 1 times 360 and divide by 2 pi. And I get I'll give you 3 sig figs, 57.3 degrees. So 1 radian is equivalent to 57.3 degrees, which is a pretty large angle. And in fact, I drew the picture up above to be roughly 1 radian. So theta in that picture is roughly 1 radian. Okay? That gives you a feeling for how big of an angle 1 radian is. Well, after all, 2 pi radians is all the way around the circle, and 2 pi is a little bit more than 6. Okay? Okay, so that's angular position with the SI unit called the radian. Now, we're going to be interested in things that are rotating about a fixed axis. And so if they're rotating, that's a kind of motion, right? It's a kind of movement. So that red dot on the wheel, like I showed you, is going around and around in a circle. So we can talk about change in angular position. And just like in chapter 2, we had change in position, we called it displacement. Now we'll have change in angular position, and we'll call that angular displacement. So angular displacement means change in angular position. So what I've drawn here is the circle and the red dot on the wheel, and the axis of rotation of the wheel that I was holding is right there in the center. And I've drawn the red dot on the wheel, 1 red dot, at 2 different times. All right, the red dot at time t1 is right here with angular position theta 1. I just so happened to draw it so that theta 1 is positive. A little bit later, at time t2, the wheel is rotated around, and the red dot is now at that second position with an angular position that I've denoted in the picture here, theta 2. So the angular position has changed between time t1 and t2. So what is the way we would define angular displacement, and what would be the symbols we'd use? Well, we want change in angular position, change in theta. So it's all Greek in this chapter. We would denote change in angular position by the notation delta theta. By definition, that means theta final minus theta initial. Or, using my picture here, theta 2 minus theta 1. Right? Final angular position minus initial. The SI unit would be the SI unit of angular position, because those theta 2, the theta 2 and the theta 1 are in radians. So theta 2 minus theta 1 is in radians. So the SI unit of angular displacement is also the radian. All right? That's just angular displacement. Next, how about some way to measure how rapidly an object is rotating about a fixed axis? Yeah, how fast, how rapidly? We had that in chapter 2 for linear motion. We called it velocity. We have both average and instantaneous. Now we're going to have what's called angular velocity. Okay, both average and instantaneous. Let's start with average. First of all, what's going to be the symbol? Not v, that's linear velocity. All Greek letters now for rotational kinematics. It is a lowercase Greek omega. Okay? Let's call it omega, not W, because it's not a Roman letter. It's a Greek letter. Clearly, the Roman alphabet was influenced by the Greek alphabet because it looks like a W to us. But it is a Greek lowercase omega. And I'm adding a subscript, AVG, because I'm defining for you average angular velocity. Here's the definition. Well, remember chapter 2. Average linear velocity, V, AVG, for motion along an x-axis, was the change in the x position, delta x, over the change in time, delta t. So we do the analogous thing here for average angular velocity. Change in angular position, delta theta, divided by change in time, delta t. And if it's referring, for example, to the picture right up above that I'm showing you here, delta theta means theta final minus theta initial, theta 2 minus theta 1, over t final minus t initial, t2 minus t1. And that's how we'll calculate average angular velocity. Just how much did theta change in a finite time interval, delta theta divided by delta t. But then we had in chapter 2, after average velocity, we had instantaneous velocity, which that was just denoted by the symbol v, and that was the derivative of the x position with respect to time. Instantaneous velocity. Now we're going to have the rotational analog. Instantaneous angular velocity. Symbol, just an omega. Defined to be the limit as the time interval delta t goes to 0 of delta theta over delta t. And by the definition of taking a derivative, that's the derivative of theta with respect to time, d theta over dt. And we say it's the rate of change of angular position, because a derivative is a rate of change. Okay, so let's remember that. Instantaneous angular velocity omega is the rate of change of angular position, d theta dt. What's the SI unit of angular velocity? Well, look at either omega average or omega instantaneous. It's got to be the unit of theta over the unit of t. So radian over second, or as we say, radian per second. Now, average and instantaneous angular velocity are vector quantities. But so were average and instantaneous linear velocity in chapter 2. How did we deal with the directions of those vectors in chapter 2? Simply with a plus sign or a minus sign. Plus sign meant that the corresponding velocity pointed in the plus x direction, and a negative value meant it pointed in the negative x direction. If average and instantaneous angular velocity are also vectors, how do we account for direction? Well, here go back to imagining the rotating wheel that I was holding about the fixed axis. It can only rotate in one of two ways as we look at it. Clockwise or counterclockwise. Right? Clockwise, the way the hands of a clock rotate, old-fashioned clock, or counterclockwise, opposite to that. So all we have to do is keep track of whether the thing's rotating clockwise or counterclockwise, and then have a sign convention. The sign convention everybody uses is this. If the object is rotating counterclockwise as we watch it, that's what this notation means. CCW is shorthand for the rather long word counterclockwise, which nobody wants to write. If, as you watch the rotating object, like the wheel, and as you watch it, it's rotating, I'm going to do it from my point of view, counterclockwise, that's a positive angular velocity. Omega is positive for counterclockwise rotation. Conversely, as I watch the thing, if it rotates clockwise, again, from my reference, that would be this way, that's a negative angular velocity. Omega is negative. So we want to remember that. Counterclockwise rotation means omega is positive. Clockwise rotation means omega is negative. Now, one other thing that may come up from time to time and is handy to remember. So I call it a tip. And that is that we can take this expression right up here. Actually, I'll write it right over here to the side. That instantaneous angular velocity is the derivative of angular position with respect to time. And we can apply the fundamental theorem of calculus, and it says, in essence, that integration is the mathematical inverse of differentiation. So the way a physicist would think about doing the inverse of omega equals d theta dt is they would multiply both sides by dt and then integrate both sides. So when I multiply both sides by dt, I'll write it right down here, I get omega times dt equals, and I just think of that side as being a d theta because the dt's cancel. And then I integrate both sides. I do the mathematical operation called integration. All right, the result of that is now the expression I'm going to refer to right over here that is useful. The integral of d theta becomes just a finite change in theta, delta theta. Theta 2 minus theta 1, change in angular position. The finite angular displacement can be found by doing this integral. Integrate the angular velocity with respect to time. Starting at whatever the time t1 is, that will be based on the problem, and ending at the time t2, based on the problem. So that expression there is the mathematical inverse of omega equals d theta over dt. All right, now we've had angular position, angular displacement, change in angular position, and then a way to measure the rate at which an object is rotating, angular velocity, both average and instantaneous. Then we had one more concept in kinematics in Chapter 2. How about some way to measure the rate at which the velocity is changing? Chapter 2. We call that acceleration. So now I want a rotational version of that. Because what if my spinning wheel's angular velocity is changing? I'd like some measure of the rate at which angular velocity changes. And that is called, surprise, surprise, angular acceleration. And we're going to have both average and instantaneous. Let me remind you from Chapter 2 what the expression was for average linear acceleration. Symbol, Chapter 2, a sub avg. It's equal to the change in the velocity divided by the change in time for a finite time interval delta t. Delta v over delta t. What's the rotational version of that? First of all, the symbol for average angular acceleration. It starts with a Greek letter. This is a lowercase Greek letter alpha, the first letter of the Greek alphabet. And I'm sorry about the fonts that all the books use, because that alpha sure looks a heck of a lot like an A. And all I can say is, please try to put in your head, it's not an A. That will cause nothing but trouble, confusion in your mind. It's not A. It's not linear acceleration in meters per second squared. It is not that. That's a symbol alpha. When I write it, I try to be a little more clear that it's not an A. I write it kind of like that. I think you can see that that's not an A. It's a Greek lowercase alpha. And if we're talking about average angular acceleration, we add the subscript avg. So what's the definition of average angular acceleration? Well, it's the rotational analog of this, the linear version of average acceleration. Except instead of delta v over delta t, change in linear velocity over change in time, it's delta omega over delta t, change in angular velocity over change in time. Or omega final minus omega initial, omega 2 minus omega 1 over t final minus t initial, t2 minus t1. That's how we'll calculate average angular acceleration. Then we had, in Chapter 2, instantaneous acceleration, A. And that was the derivative of the velocity with respect to time, dv dt. What's the rotational version? Instantaneous angular acceleration, just a symbol alpha. And is defined to be the limit as the time interval delta t approaches 0 of delta omega over delta t, but by the definition of derivative, that's the derivative of omega with respect to time, d omega dt. And we call that the rate of change of angular velocity, because a derivative is a rate of change. Okay? Now, what's the SI unit of angular acceleration, whether you're talking about average or instantaneous? It's the unit of angular velocity divided by the unit of time, in SI. Angular velocity unit, remember, is radian per second. Time, of course, is second. So the SI unit of alpha is radian per second, or radian per second squared. Well, remember in Chapter 2, for linear acceleration, it was meter per second squared. Now for angular acceleration, take out the meter and put in radian. It's radian per second squared. Okay, here's a rather important thing to emphasize when you're talking about a rotating rigid body, like the bicycle wheel I've been showing you, or I showed you. And the question is this: what does the sign of the angular acceleration tell us about the rotational motion? Let's step back a minute. Let me ask you this. What does the sign of the angular velocity, omega, tell us about the rotational motion? And we just said in the previous slide, the sign of the angular velocity tells us simply which way the thing is rotating. If angular velocity is positive, I know the thing is rotating counterclockwise as I view it. If the angular velocity is negative, the object is rotating clockwise. So the angular velocity tells me which way it's rotating, counterclockwise or clockwise. What does the sign of the angular acceleration tell us? Well, let me go back to Chapter 2 again. What did the sign of the linear velocity tell us? V. Simply the direction of motion, plus x or minus x. What did the sign of the linear acceleration tell us about the motion? We have to go back a minute, but what it told us was whether or not the particle was speeding up or slowing down in its motion, going faster and faster or slower and slower. And how did we know that? If the velocity and the acceleration, v and a, had the same sign, the object's speeding up. And if the velocity and the acceleration had opposite signs, one positive and one negative, it's slowing down. Same thing here for rotational motion, okay? If the angular velocity and the angular acceleration have the same signs, either both positive or both negative, the object is speeding up. That means it's rotating faster and faster. If the angular velocity and the angular acceleration have opposite signs, one is positive and the other is negative, then the object is slowing down, rotating slower and slower. That's really useful to remember in this chapter. But it's just this rotational version of the same idea from Chapter 2. And let me give you now the same tip I did on the previous slide. There is a way to find the change in the angular velocity if you know the angular acceleration. And it follows by taking the definition of instantaneous angular acceleration as being the derivative of the angular velocity with respect to time, d omega dt. Multiply both sides by dt. You get alpha dt on the left and just d omega on the right, and then integrate both sides. And the result is over here. The finite change in the angular velocity, omega 2 minus omega 1, can be computed by integrating the angular acceleration from some initial time t1 to a final time t2, where those times will be determined by the problem we're solving. Okay? All right, so that's another useful thing to remember. All right, let's go right to some practice, and then that will be all for this video. So let's practice with rotational kinematics a bit. Okay. Sorry that that's a little bit out of view there. There we go. Is that better? Hopefully that's better. Okay. So here we go. Suppose that you work at a company that designs and manufactures vintage spinning wheels. Your customers are people who are interested in spinning their own yarn from natural fibers. So it's a wheel that spins about a fixed axis. The motion of such a wheel is animated in the animation I'm going to show you in a second here on Wiley+. And we'll run it so that you can see. The wheel will rotate in the XY plane with its center, its axis of rotation, at the origin. There'll be a dashed radial line on the wheel that's initially along the fixed x-axis, and so therefore the initial angular position of that line will be known. Then the angular position of that radial line on the wheel versus time is plotted. You'll see it there. And the red dot on the wheel and the blue shading that you'll see in the background are meant to be guides to the eye. Okay. I'm back. I had a little technical issue. I believe it's solved. So let me now go to Wiley+. Let's see. So, okay. I've gone now to Wiley+, and I'm showing you now the animation. At least you can see it at what we'll call t equals 0. You can see the spinning wheel. The axis of rotation is at the origin. Look carefully, you'll see a black dashed line going out to a red dot, and that's initially lined up with the plus x-axis. Okay, all I'm going to do is, for now, just run the animation. I'll maybe run it a couple of times so that you can see the motion, and then we're going to start answering some questions. Here we go. Watch the red dot and the black line. That's what we want to keep our eyes on. The x and y axes are not moving. Okay, so it did something rather interesting. Let's watch it again. It's going around clockwise as we view it, but it's slowing. Oh, it stopped for an instant. Now it's going counterclockwise and clearly speeding up. All right, so that's the motion I want us to think about. Okay. All right, let me read to you the first question we're going to answer here. I'll show it to you. It's a multiple choice. Number 1, which of the following statements is the most accurate depiction, or description, I should say, of the wheel's motion at the instant t equals 0? With 4 options. A says that the angular position is equal to 0 and the angular velocity is greater than 0. B, the angular position equals 0 and the angular velocity is less than 0, negative. C, the angular position is greater than 0 and the angular velocity is equal to 0. D, the angular position is less than 0 and the angular velocity equals 0. I'd like you to try that for yourself. Pause the video, of course, if you wish to do so. Think about it, please, and then come back. Okay, welcome back. Let's go back and look at the animation. That is the t equals 0 situation. There's even a graph there, isn't there, in the upper right corner of the angular position theta. We divided it by 2 pi, just to make nice simple numbers on the y-axis, versus the time t in seconds. And so that blue curve is the angular position as a function of time. And there's a red dot on it that shows you where you are on that graph as a function of time. So if I run it again, you can see the red dot move along the graph as the wheel rotates. Fine. But let's go back to time 0. Clearly, the picture and the graph show that the theta is equal to 0. So the answer must either be A or B, because those are the only ones that have theta equal to 0. So which is it, A or B? Well, it depends on what the angular velocity is. Is it positive or negative at this instant? Well, even though this was, this is a freeze frame at t equals 0, when this freeze frame is drawn, the wheel was in the process of moving, rotating. Which way was it in the process of rotating? Clockwise or counterclockwise? Well, the animation told us it was going clockwise, right? So theta 0, the clockwise rotation means angular velocity omega is negative. Note another way to see that. That means, by the way, that the answer is B, of course. Okay? Theta is equal to 0, and the angular velocity is negative. At the instant t equals 0, that's what we're talking about. Another way to see that the angular velocity is negative is to look back at the animation, and if you look carefully, I'll change the time slider maybe so you can see. With the red dot is a short, straight, black dashed line. That is a guide to your eye to show you the tangent line to the theta plot. And remember, the slope of that is the derivative. Slope of the tangent line is the derivative, and the derivative of angular position is angular velocity. So the slope of that little black dashed line segment tells you the sign of the angular velocity, and that slope, even at time 0, is negative. Okay, so initially the angular position is 0, and we have clockwise rotation, so the angular velocity is negative. Next question. We're supposed to reset the animation. Fine, we can do that. And select the option, Show Angular Velocity Plot, and run the animation again. We're going to be asked about the most accurate description of the wheel's motion at t equals 0. So more about what's happening at t equals 0. So it's reset. I'm going to click Show Angular Velocity Plot. Aha, there's a new graph with omega in radian per second on the y-axis, t in seconds on the x-axis. Still going to move in the same way, but now the omega graph is also providing me information. All right, and it's back to asking me about what's happening at t equals 0. So let me bring the slider back to time 0. And now I have the angular position plot to look at and the angular velocity plot to look at. The options are, which is the most accurate description of what's happening at time 0? A, the angular acceleration is positive and the wheel is speeding up. B, the angular acceleration is 0 and the wheel is turning with constant angular velocity. C, the angular acceleration is positive and the wheel is slowing down. D, the angular acceleration is negative and the wheel is speeding up. Which is the best answer? I'd like you to think about it, please. Pause the video and then come back. Okay. So, let's refer back to the animations. And clearly question 2 is asking us to focus on angular acceleration, alpha. But remember, angular acceleration, alpha, is derivative of angular velocity with respect to time, d omega dt. But I've got a graph of omega versus t. So the slope of the tangent line to that graph is alpha. So if the tangent line has a negative slope, alpha is negative. If the tangent line on the omega graph is positive slope, then alpha is positive. Again, we're talking about the instant t equals 0, which is where I've got the slider. So look at the angular velocity plot. Look at the red dot on it, and look carefully. There's a little black black line segment, or little colored line segment there, I think maybe it's blue, that is tangent to the omega curve. And the slope of that tangent tells you the sign of alpha. So what's the slope of that tangent on the omega graph at time 0? That tangent line has a negative slope. That means I know that the angular acceleration at time 0 is a negative quantity. Well, that must then determine what my answer for question 2 is, right? Because the only one that shows the negative angular acceleration is D. Now let's make sure we understand the rest of that statement in D. It says, and the wheel is speeding up. You see why that's true? Remember how you know if a wheel is speeding up as it rotates? The angular velocity omega and the angular acceleration alpha have the same sign. We already said in question 1 that at time 0, the angular velocity is a negative quantity. And we now just said at time 0, the angular acceleration is also a negative quantity. So yes, it's speeding up. In fact, what's happening at time 0 is that the wheel is rotating clockwise and speeding up. Okay? All right, let's go on to question 3. Is the angular acceleration of the wheel constant? That's a yes or no. I'd like you to try it for yourself. Pause the video, think about it, and then come back. Okay, let's go back to the graphs that we have in the animations. And let's look again at the omega plot, omega versus time. Remember, the slope of the tangent line on that graph is alpha, angular acceleration. So the only way to have the angular acceleration be constant is to have a graph that has a constant slope. Such a graph is a straight line. Therefore, I need the angular velocity graph to be a straight line. Then the angular acceleration will be constant. Is the omega graph a straight line? No, it's not. It's the slope of the theta graph. But the omega graph is not a straight line. So the angular acceleration is not constant. So that means that the answer to question 3 is no. That's all you have to say, no. All right, question 4. At which of the following moments in time does the wheel change from speeding up to slowing down? Because we know at time 0, it's rotating clockwise and speeding up. But we also saw, if you remember in the video, that there was a time interval when it was slowing down, and even one time when it stopped for one instant, and then it went back around counterclockwise. So what I want to know is, which of those times, in those 4 options, they're all 4 t values, does the wheel change from speeding up to slowing down? Now, in order to help us answer that, I've reset the time slider 0. I'm going to click this last button and add one more graph, the angular acceleration plot versus time. Alpha in radian per second squared on the y-axis, and time in seconds on the x-axis. And that alpha graph is the slope of the tangent line of the omega graph, because that's going to help us. Okay? All right, let's take these 4 times that it gives us and see if it's the moment when the object changes from speeding up to slowing down. All right, or actually, let's do it this way. Let's do time intervals. Let's look at the omega graph and the alpha graph together. If the omega and the alpha have the same sign, it's speeding up. If the omega and the alpha have opposite signs, it's slowing down. So look for time between 0 and just a little past 2 seconds. That time interval, between 0 and a little past 2 seconds. The angular velocity omega in that time interval is negative, and the angular acceleration is also negative. So what I can say, I'll come back over here, and I'll write right underneath here that for the time in that interval, the angular velocity is negative and the angular acceleration is negative. So it's speeding up. Okay, I know that for sure. Let's go back to the animation. Now, let's look between, it turns out that's 2.1, by the way, where that changes, where the alpha is 0. Now let's look for the time between 2.1 and a little past 6 seconds. Turns out it's 6.7 seconds. Between 2.1 seconds and 6.7, the angular velocity is still negative, but the angular acceleration is positive. Let's write that down. Okay? For the time interval t between 2.1 and 6.7 seconds, the angular velocity is negative, and the angular acceleration is positive. Note, even though the angular acceleration is positive, because it has an opposite sign to the angular velocity, during this time interval, it's slowing down. Aha, so do I see then where it changes from speeding up to slowing down? I think I do. It's speeding up until 2.1 seconds, and then from thereafter, at least up to 6.7, from 2.1 to 6.7, it's slowing down. So this 2.1 seconds is right at the boundary between speeding up and slowing down. That's where it transitions from speeding up to slowing down. So the answer must be B. 2.1 seconds is where it changes from speeding up to slowing down. Let's look at one more time interval just to be thorough here. Back to the graphs. Now let's look from a time 6.7 seconds onward, thereafter. In that time interval, omega is positive and alpha is positive. Both are. So the way I'll denote that is I'll write this. For t greater than 6.7 seconds, the angular velocity is positive and the angular acceleration is positive. So it's speeding up again. But I was asked for the moment it transitions from speeding up to slowing down, not the other way around. So the answer is 2.1 seconds. So the wheel is initially speeding up, then it slows down, stops for an instant, and then it speeds up again. That's what is happening in that particular situation. Okay, I'm going to leave you today with a class engagement exercise to do on Blackboard, which is just more practice with rotational kinematics. Let me write this, and then I'll read to you what it says. Okay, class engagement on Blackboard. We've got a table provided here. It indicates the initial direction of rotation, CL for clockwise and CC for counterclockwise, for a body that experiences a continuous angular acceleration. Okay, that's this column right here, initial rotation. CC for counterclockwise, CL for clockwise. The sign of the angular acceleration is also indicated. That's this column. Positive or negative? Fill out the last column right here to indicate if the rotation will continue in the initial direction. You would say no reversal, or eventually be reversed. Say reverse. So the answers on each of those squares in that last column are either no reversal or reversal. And of course, reversal means that it changes its rotation from one sense to the other, from clockwise to counterclockwise or counterclockwise to clockwise. No reversal means it never changes. It's always going around the same way. So you just write your 4 answers for each of those 4 cases, right? Just in order, 1, 2, 3, and 4. Okay, that will be our engagement exercise. There'll be another class video in which we will continue to practice with these ideas, but that's all for this first video.